So in this class, we will continue with the basic logic gates, the simple question from chapter number 2, as well as it covers chapter number 3 also. For exam point of view also, this in both the chapters it is important, especially in third chapter, this is one important question, all right? So we'll start with that is basic logic gates. If you study thoroughly in this, no need to study in the chapter number 3, right? 2 we will complete now here only, right? Okay. Say, basic logic gates is the heading. In the chapter 2 itself, we have used one name called as Claude Shannon. Practically has implemented this Boolean algebra in a telephone switching circuits, right? That realized the Boolean algebra could be applied to computer electronics as well. So in the beginning only I stated that today this is the backbone of our computer industry also, the logic gates. In the computers, the Boolean operations are performed by logic gates. That's why now we'll study about the logic gates. The first one mark question you may get in account to chapter number 2, or in chapter number 2 there is no one mark question, but in chapter number 3 related this is important for one mark question, right? So what is a logic gate? So before defining that, just you can understand here the terms. Gates are digital. Gates are digital circuits because the input and output signals are either low voltage, that will be denoted by 0, or high voltage, that will be denoted by 1. That's why the digital circuits are two-state circuits, either 0 or 1. Gates are often called logic circuits because they can be analyzed with Boolean algebra, right? By knowing these terms, that is low, high, 0, 1, 2 state, right? Now we'll define what is a logic gate. A gate, logic gate is a gate, is an electronic circuit. Logic gate is an electronic circuit which operates or which takes one or more inputs, signals, and produces an output signal. It means logic gate is an electronic circuit which takes one or more input signals and produces only one output signal. Such gates we are calling it as logic gates. A gate which operates on one or more input signals and produces one output signal. That gate is nothing but a logic gate. So after knowing this particular definition, logic gate, now we move on to the types of logic gates. The logic gates are broadly classified into two types. That is, one is called as basic logic gates and derived logic gates, fundamental gates and derived gates. But right now in this chapter, we are studying only the basic logic gates. That is, in the logic gates, that's why I say that we are not confusing you that the third chapter, that is division, is mentioned, but in this second chapter, in this chapter, only logic gate is there. That details about that is not mentioned here. That's why we are starting with the gates are of three types, basic logic gates, right? These three are nothing but basic logic gates. They are NOT gate, OR gate, and AND gate. NOT, OR, AND. These three are called as basic logic gates. Now, we'll study one by one in detail, right? So, to explain any of these gates, the concept you have to remember that to explain any of these gates, each and every gate will be explained in three parts. First, we should know the logic symbol of that. Then secondly, the truth table and explanation. It means in 3 parts we are explaining each and every gate here. Right? Okay. Now, we'll start with the first gate, that is NOT gate. It is also called as inverter. A NOT gate is a gate with only one input signal. This is the only gate. It accepts only one input signal and produces only one output signal. A gate which takes one input and produces one output is nothing but a NOT gate. And the output of this gate is always the opposite of the input signal. That's why it is called as inverter. It complements the given input. An inverter is also called a NOT gate, or NOT gate is also called an inverter, because the output is not the same as the input. Always the output is reverse of the input. Suppose if the input is low, output is high. Suppose if the input is high, output is low. That's why it is also called as this gate produces output as the complement of the given input. For example, if you check here in the truth table, x and x complement. NOT gate representation output is complement because it is invert. If the input is low, right? If the input is low, then see here, if the input is low, then output is high. If the input is high, then output is low. Either you can use these words low and high, or else you can go with the logical values, that is 0 and 1. If your input is 0, then the output will be 1. Right? Low, high, off, on, like this. Then if the input is 1, then the output is 0. Right? A low input or 0 produces high output, or 1 and vice versa. And you should remember that in the beginning only I told that to explain any gate, that will be explained in 3 parts, that is explanation, truth table and symbol. Now 2 parts we have completed, that is explanation is over, truth table is over. Now the symbols, see this is the symbol, logic symbol. NOT gate, logic symbol, that is one triangle and a bubble. This x is the input, then the output will be x complement, that is inverter, or complement. The given input will be complemented, that is nothing but the output of NOT gate. I hope you understood this. Then next, after knowing NOT gate, now we move on to the OR gate, right? The OR gate has 2 or more input signals. OR gate has 2 or more input signals, but only one output signal. This is the first point. It takes 2 or more input signals and produces only one output signal. This gate gives the logical addition of the inputs. It means the OR gate performs logical addition operation. Whatever the input you are giving, that will be logically added. It performs logical addition operation. That is point number 2. If any of the input signal or both is 1, the output is 1. When you get output as high, either all the inputs are high, then the output is high, or if any one of the input is high, then the output is high, because it performs logical addition operation. An OR gate can have as many input as desired. No matter how many inputs are there, the action of OR gate is the same. We are not worrying about any number of inputs here. But one thing you can keep it in mind, that we need 2 or more here. At least we need 2 inputs. More than that, welcome. Right? Then if you observe the truth table here, after knowing that theoretical part, you come to know that, say, if x and y are the inputs, then f will be the output. Here f is nothing but x plus y, that is x plus y is nothing, this plus is nothing but Logical addition, not mathematical, logical addition. You come to know now here. See here. If x is 0 and y is 0, then f is also 0. That is, f is nothing but x plus y. X plus y is also 0. X is 0, y is 1, then f is 1. Then x is 1, y is 0, 1 plus 0 is again 1. Now check it here to understand the meaning of that logical addition. X is 1, y is also 1. Then output is also 1 because logical addition. True plus true is true only. 1 represent true, 0 represent false. True plus true is true. 1 plus 1 is 1. That's why I said that in the beginning itself you are repeating that it performs logical addition, not addition, logical addition. Only addition means 1 plus 1 is 2, but logical addition 1 plus 1 is 1 only. This is about 2 input OR gate truth table. If it is a 3 input OR gate truth table, that is given here, right? You write the binary numbers in 3 bits in different combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. It means it started from binary 0 to 7. 0 to 7, 3-bit binary number written in a different combination. That is the permutation combinations. Right? Then check out the logical addition. 0 plus 0 plus 0 is 0. 0 plus 0 plus 1 is 1. It means when you observe the outputs here, all the outputs are 1 because in each and every combination there exists 1 or more than 1 as a input. That's why the outputs are 1. It shows that if you observe 2 input and 3 input truth table, you can conclude that when you get 0 as an output in OR gate, if and only if all the inputs are 0, then the output is 0, otherwise 1. See here also, if all the inputs are 0, output is 0, otherwise 1. This is the impact statement on truth table of OR gate. Then the logical representation or logical symbol of OR gate is here. This is the 2 input OR gate. A and B are the 2 inputs. F is the output. Here it is A, B, C, 3 input OR gate. Right? Then 4 input OR gate symbols. These are logical symbols. At least you should remember 2 inputs and 3 inputs. This completes OR. Then we move on to the last gate, right? That is AND gate. One dialog point is there here. That is, it is a dialog because it is applicable for all the gates except the NOT gate. The AND gate also takes 2 or more input signals and produces 1 output signal. This is the dialog point. This point is applicable for all the gates except NOT gate. When all the inputs are 1 or high only, then the output is 1. In the AND gate, if all the inputs are 1, then only you will get output as 1. It is exactly reverse of that. If all the inputs are 0, the output is 0 in case of OR gate, whereas in case of AND gate, if all the inputs are 1, then only output is 1. Because in the AND gate, this AND gate performs logical multiplication operation. The AND gate performs logical multiplication operation. If any one of the inputs are 0, then definitely the output is 0 because 0 multiplied with anything is 0. That's why this point is very important again. When all the inputs of this gate are 1, then only output is 1, otherwise 0. So this is about the explanation. Then we move on to the truth table and logic symbols here. Truth table of 2 input AND gate, 0, 0 is 0, 0, 1 is 0, 0 into 1, multiplication, logical multiplication, false into true is false, that is 0, true into false is false, that is 0, 1 into 0 is 0, but 1 into 1 is 1 here. 1 multiplies with 1, that is logical multiplication. True into true is true. It means if all the inputs are 1, then only output is 1, otherwise 0. That is shown in two input AND gate. Same thing can check out with three input AND gate. See, observe, when you observe here, the outputs is a logical multiplication x into y into z, right? Is the output of three input AND gate. If you observe, all the cases are zero except this one, last one. We are getting this one as output here because all the inputs are one. That's why the output is one, otherwise zero. Now check out the logical symbol, just like a D, right? Two inputs A and B, one output, that is F, F equal to A dot B. Three input logic symbol A, B, C, F equal to A dot B dot C. Four input AND gate, F equal to A dot B dot C dot D, right? So this is about the basic logic gates, right? I hope you understood this, right? Then if you understood this, share this video to your friends and subscribe it, right? Thank you one and all.